But thank you everyone for joining our webinar today. Today I have Christy Rosati. She's a field application engineer from Bussmann, and she will be going over the first part of the three-part series. And today will be equipment short circuit current ratings. So Christy, whenever you're ready, you can go ahead.
All right, thank you very much. Again, my name is Christy Rosati, Field Application Engineer for the Bussmann Division. We're going to have a three-part series here on equipment short circuit current ratings. Today is going to be the shortest of those three presentations. We're really just going to talk about the codes that govern short circuit current ratings, basically explaining why it's important. And then in the future, we'll go into some of the nitty-gritty of how we calculate it. We'll get into all of the weeds there. So here's our web series right here. So part one, the codes and the applications. Two will be next week. That's going to be determining SCCR with UL 508A, supplement SB. And then part three will be strategies for increasing the panel short circuit current rating. I do want to just mention at this point, if you have any questions during this presentation, please feel free to either take yourself off mute and ask a question or ask it through the chat. I want this to be interactive. This is all for you. So our agenda, we'll talk a little bit about short circuits, basically why we protect ourselves from them. We'll talk about short circuit current ratings, interrupting ratings, and then the codes and standards governing short circuit current ratings. So first and foremost, right, a short circuit or a fault. The NEC uses, it used to use short circuit and fault interchangeably, and in the 2020 version of the NEC, it's actually standardized on the term fault current. So when you see fault current, a short circuit, those are the same thing, but the NEC is now always going to refer to it as a fault current. And a fault is a severe overcurrent, right? It's a result when the current flows outside the normal circuit path. So that means it could be between phases, it could be between phase and ground, and it can be up to 200,000 amps. It can be, hundreds of thousands, tens of thousands of amps higher than the normal full load current. My effects of short circuits, pretty dangerous stuff here, right? Insulation damage, fires, explosions, vaporizing conductors, vaporizing metal, warped bus bars, some literally violent stuff here. So we want to make sure we protect ourselves. The very classic example of a short circuit that we use here is going to be the screwdriver between the two conductors, right? So in this scenario, when I have that screwdriver go between those conductors, my electrons would normally go, from my source out to my load and back to my source. But they're lazy. They don't want to go out to that load and do work if they don't have to. They're going to take that shortcut through the screwdriver. This essentially takes my load out of the circuit. And the vast majority of the resistance in my circuit is in my load. So if I take the load out of the circuit, that means I take most of the resistance out of my circuit. And if I look at my Ohm's law, which I have in my top right-hand corner there, my short circuit current is equal to the voltage divided by the resistance. You can imagine if that resistance starts to drive towards zero, it's obviously not going to get all the way to zero, but it can get pretty close during a short circuit. And the voltage is staying constant, I can get some really, really high values for that short circuit current. So that's why when my current is flowing outside the normal path, when I bypass my load, I can get some really, really high values for short circuit. And I want to make sure I protect myself from them. My sources of short circuits, so where are all of those electrons coming from when I have a short circuit? The utility is typically by far the largest source of my short circuit, right? That's where most of the available energy is from. I may have a generator or some sort of alternative energy source. Those can also add in short circuits. It's usually a lower value than what you get from something like a utility, but they can still develop short circuit currents. Sometimes like a UPS backup system as well. Again, a much lower value of short circuit available from them, but there is a value associated with it. And then the only thing that's on, sort of either your end user end or customer end is going to be the motor load. So motors can actually add short circuit back into the system. So if you have a large amount of motors during a short circuit, they can actually essentially become generators and feed current back into the system. So those can be a source of the short circuit current as well. In the 2020 NEC, we actually got these handy dandy definitions of fault current. So this is sort of the first time, and there's been a standardization in the language in the 2020 NEC around the term fault current here. So it's not short circuit current anymore. It is fault current everywhere in the 2020 NEC. Fault current is the current delivered at a point on the system during a short circuit condition, and available fault current is the largest amount of current capable of being delivered at that system. So sometimes this is called, the maximum available fault current, the maximum short circuit current. Now it just means if you see available fault current already means you're at that maximum short circuit condition. That is going to be your worst case. That is your available fault current. We also got this informational note figure in the 2020 NEC that helps us sort of describe where these are. We've got our source. Right at the secondary of that source, we're going to have an available fault current. We're going to have another available fault current at the end of the conductor that's going to attach me to my equipment, right? That equipment's going to have a short circuit current rating. Inside that, it might have an overcurrent protective device with an interrupting rating. And then I'll have another available fault current right downstream from that. So anytime you have those impedance components, you get a different available fault current at each of those points on the system. So my fault currents can change, so it's really important that I update any sort of fault current studies periodically. A lot of times the source of my fault current could change, so maybe the utility changes out the service transformer, or just something in their service line to you. This one's tough because a lot of times they don't actually let you know when that happens. So the utility could change the service, or you can add more motors to your system or modify the power distribution system, right? You can have longer conductor lengths, shorter conductor lengths. Maybe you moved a piece of equipment from one part of the plant to another part of the plant, and the available fault current is different over there. And then, fault reducers can change. So again, that's my conductor lengths changing due to moving things around, and maybe, customer owned transformer, right? That can change out. You put in a high energy, there's all those high efficient transformers out there now. Those are great. But high efficiency transformers will wind up giving you a higher available fault current because they have lower impedances, which is absolutely great for power efficiency, but will result in a higher available fault current. So system analysis studies, any determination of what fault current is should be updated periodically. Definitely when major system changes occur. What I typically recommend here is, so calculating fault currents is usually, it's a step in the process of an arc flash study. So it's not the same thing as all of your arcing currents and incident energies. But it's a step in the process of calculating that. So if you do an arc flash study every 5 years, like OSHA recommends, then you should also be updating all of your available fault currents every 5 years as well. So that's probably sort of the easiest way to do it. Or again, if you have a major system change, you want to update it when that change is made. So some typical values for short circuit currents that we can see out there. So at a home receptacle, we're looking at about 200 to 500 amps, which is, relatively low compared to what else is on this screen. But certainly still a whole lot of amps. Our home service, right? So this would be sort of a typical, residential single family home standalone. 2,000 to 10,000 amps, pretty typical. If you're talking about, an apartment building, you might get up to about 25,000 amps, particularly in a downtown area. Light industrial, that's where we see that 65 kA, 70,000 amps, around that range. Heavy industrial easily can get up to 100,000 amps. And then in a large city, you can exceed 100,000, and you might even exceed 200,000. I believe the typical available fault current in the downtown and center city Philly area is in the 100,000 amp range. New York City, DC, Boston, they definitely exceed that on a regular basis. But high fault currents, they're definitely out there, and they're extremely destructive, so we want to make sure we're protecting ourselves from them. So my fault calculations, right, how I determine this available fault current, I use the voltage short circuit current. So most of the time we're talking about a three-phase voltage short circuit. And I use that to determine what interrupting ratings I need and my short circuit current ratings. I also use it for selective coordination. That's not something we're going to go into during any of this. That has more to do with emergency backup systems and things like that. That's just another thing that we need that value for. And it is different than arcing faults. So a lot of times we can think of arc fault as like arc flash. That's the worst thing that can happen to you, right? Well, I mean, they're really bad. They're really destructive. But the actual amount of current that goes through an arcing fault is less than my voltage fault current, right? And that's because when you think of a voltage fault, right, that's minimum resistance going through there. Arcing fault, that's actually, right, that's your electricity. That's going through air. And there's more resistance in the air than there would be in a conductor. So an arcing fault is typically between about 40 and 60% the value of that available fault current. So the available fault current is higher. We still use arcing fault to determine arc flash energy, PPE, safe work practices, things like that, but it is a separate calculation in addition to that available fault current. So with that, we can finally talk about short circuit current rating. So short circuit current rating, or SCCR, what is it? Short circuit current rating is the prospective fault current that an apparatus or system can be connected to without sustaining damage exceeding defined acceptable criteria. And that last part, that's, you know, my favorite part, right? Without sustaining damage exceeding defined acceptable criteria. What does that mean? Who decides what that acceptable criteria is? How much damage is acceptable? So generally, to pass your short circuit current rating test, it means that during a short circuit of that amount, you cannot create a shock, fire, or projectile hazard. So a short circuit current rating does not mean that the equipment will be able to be used again after experiencing a short circuit. It just means it's not creating a shock, fire, projectile hazard. When we talk about shock hazard, that's typically conductors pulling away from terminations, right? The enclosure could become energized. You just have, you know, live conductors floating around. That's a bad thing. You're not allowed to have that. Fire hazard, so any sort of explosive power that blows off the door and exposes the flames. Fun fact, you can create a fire, and if the door doesn't open and expose you to the flames, you've passed that part of the fire hazard. This is where I usually emphasize, remember, doesn't mean you necessarily will be able to use it again. So you can have an adequate short circuit current rating and still create a fire within the enclosure. And if it doesn't open the enclosure, you know, you've still met the requirements for short circuit current rating. There's another type of rating called type 2, no damage protection. And that means that there is a guarantee that you'll be able to use it again after a fault. And that's not the same thing as short circuit current rating. That's sort of an extra level of protection. Short circuit current rating just means no shock, fire, projectile. And that last one, projectile, that's pretty self-explanatory, right? Enclosure door opening, exploding, you know, shrapnel, debris. So we don't want to create a shock, fire, projectile hazard. If we don't create a shock, fire, projectile hazard, we have a short circuit current rating. Short circuit current rating is typically going to apply to an entire apparatus, right? So to an assembly. And my assembly will have a short circuit current rating, my industrial control panel, my industrial machinery. So, right, everybody's favorite part of Bussmann presentations usually are misapplications. So here's a misapplication of short circuit current rating. So we have a combination motor starter with 5,000 amp short circuit current rating, 50,000 available spot current. I believe this is at 480 volt, and we'll just see what happens to this combination motor starter. My favorite part is that at the end, like whoever was recording this. So I've got some still frames of here, and you can see right here at 0.01 seconds, it's done, right? It's already, you know, has not met its requirements of not creating at least the fire hazard already. And that makes sense, right, when we think about it, because the very worst part of a short circuit is typically going to be that first peak. right? And if we have an asymmetrical short circuit, which, you know, we have symmetrical short circuits in a lab. In the real world, we have asymmetrical short circuits. So that first peak, that first half cycle is going to be the worst cycle, right? It's going to be the most amount of energy that goes through. So you know instantly whether you have passed or failed that short circuit test. Because right here you can see at that 0.01 second, it's done for. You can see the fire, the explosion, that door opening, hanging on by a hinge. That is not going to pass. Definitely not passing the fire or the projectile part. And if there's any loose conductors in there, then the shock hazard is done for as well. So it's, one really, really important thing to remember about short circuit current rating is that it is not the same thing as interrupting rating. Interrupting rating and short circuit current rating get confused a lot. And I think it's because they're in the same units, right? They're both in KA. But they mean something very different. So the interrupting rating applies to an overcurrent protective device. Overcurrent protective device, most of the time we're going to be talking about a breaker or a fuse, right? So a breaker or a fuse have an interrupting rating. And these are the devices that actually do something when there's an overcurrent, right? The breaker trips, the fuse opens. And the interrupting rating is the highest amount of current that it can interrupt, right? Because this is the device that's actually clearing that fault. So, right, the interrupting rating, this actually applies to a device that is physically doing something, you know, during that short circuit. So I have an NEC requirement for interrupting rating. 110.9 tells me that, you know, all of my interrupting ratings should be basically greater than or equal to the available fault current. That makes sense, clearly. Really, another important thing to note about the interrupting rating is that the interrupting rating is a self-protection rating only. So if I'm a breaker and I have a 35,000 amp interrupting rating, it means that if the breaker, if I see 35,000 amps, I'm going to trip and I'm going to be okay. I'm going to clear that fault and be safe. But I'm not guaranteeing the protection of anybody around me, right? That's where high fault ratings and things like that come into play. That's where the short circuit current ratings come into play. Interrupting rating, though, is only the rating for that device, a self-protection rating for that overcurrent protective device. The interrupting ratings for breakers can change depending on the voltage at which we apply them. The interrupting ratings for fuses, you have an interrupting rating that is valid all the way up into the maximum voltage of that fuse. So a lot of times we think 600 volt fuse, one interrupting rating all the way up until 600 volts. Sometimes there's a separate rating if it's a DC voltage, but usually it's again, it's going to be up to that maximum DC voltage, one interrupting rating. Breakers interrupting rating change depending on the voltage. So interrupting rating, also very, very important. Another video to show you why. So in this video, you can see we've got this 2-pole 15 amp multiple-phase circuit breaker, has a 14,000 amp interrupting rating. We're at 480 volts here, and we're going to hit it with 45,000 available fault current, and we're just going to see how this breaker handles it. This part's actually in slow motion. You'd believe it. You could tell here. It's like the Death Star exploding there, right? In slow motion. So, you know, this breaker interrupted the fault current, right? There's no more current flowing through there. But that's not a safe interruption of the fault current. So it's a violation, certainly, of some NEC and OSHA codes there. So here's some still photos. You can see that breaker's actually trying to open. You can see arcs coming out of that arc chute. It's trying to cool it off, but way too much energy for it to be able to handle. And we get the kaboom that we see with that breaker. So how we actually determine short circuit current rating, we talked about short circuit current rating, we talked about how it's different than interrupting rating. How do we actually come up with this value for SCCR? There's really two methods. One is short circuit testing in a high power laboratory, right? This is, you build a piece of equipment, You ship it to UL, you pay them a lot of money, they zap it with a lot of current. If it doesn't create a fire, projectile, or shock hazard, you have a short circuit current rating for that piece of equipment. This is a fantastic method of figuring out short circuit current rating if you build the same thing over and over again, right? Because you can build it once, test it once, and have a listing that'll work for all of your products. Unfortunately, within an industrial control panel type environment, we usually build something different, something custom every single time. So it's not practical to do a high power test on that piece of equipment every single time. So we have an analysis method for that. That's UL 508A. Supplement SB in particular is what details the method for determining the short circuit current rating of that piece of equipment. And that is what we will go much, much further in depth on next week. On how we actually determine the short circuit current rating using this method. So why is SCCR important? First and foremost, safety, right? We saw videos of what happens when we do not have adequate short circuit current rating, and I don't think any of us want to be standing in front of that piece of equipment when it does not have adequate short circuit current rating. So safety, number one. Number two, right, codes. So there's actually a variety of codes. We'll talk about sort of each of these individually here. The first one's OSHA, right? OSHA says we have to provide a safe working environment. Part of providing a safe working environment means that all of the equipment is rated to handle the available fault current, right? So if I'm the end user, right, if I'm the person who actually owns that piece of equipment when it's in use, OSHA is probably what I care about the most. NEC is the installation code, right? The National Electrical Code is an installation code. So if I am the installer or the authority having jurisdiction, which, that might be an electrical inspector, that might be the end user, again, is their own authority having jurisdiction. They're going to care the most about the NEC, right? You have to meet the requirements of the NEC to be able to install, and power up equipment. And there were some changes made to the NEC, some additions in 2017. We'll go over some of those for a lot of pieces of equipment regarding short circuit current rating and available fault current. And then finally, the last one is going to be UL, right? So if I'm the manufacturer of the equipment, I care about UL because that will determine the procedures for how we, figure out what that SCCR is of the control panel. So that's UL 508A for identifying control panel short circuit current rating. So let's talk a little bit about the NEC and some of those changes that occurred, that really make it, it's really made short circuit current rating sort of even more visible than it used to be. So the SCCR is supposed to be marked on your nameplate, quote unquote, plainly visible. Generally, that's been meant that inside of the door or on the outside. That's not new. That's been in the code since the 2005 cycle. Do not install where the SCCR is less than the available short circuit. That's not new. That makes sense. What was new, what was added in 2017 is actually a requirement to determine the available short circuit current. Data provides documentation to your AHJ. And the reason that is because, right, that last piece, do not install where the SCCR is less than the available short circuit current, that is not enforceable unless you know the available short circuit current. So they're not really changing the intent of the code here. What they're doing is adding in a method to enforce a code that already existed. They're actually requiring that you know the available short circuit current. And this is usually where I get a question about, well, whose job is it to determine that available short circuit? Is it on me, the builder of the panel? Probably not, right? So the available short circuit is going to be different in every single scenario, right? Every single system is different. It's got its own sources and impedance in between itself and the source of the short circuit to determine that. So it's really on the end user to be able to either provide the information to be able to determine that or to determine that information themselves. Maybe the installer can do it. So if there is a contractor associated with a large facility, they might be able to do that piece of that information But, you know, a lot of equipment manufacturers, they do their own installations, and so therefore you might not know it. But it's really going to be on the end user, I would say, to be able to provide either the information to be able to determine that, or to be able to determine that information themselves. The big thing is that that piece of information is the responsibility of the installer. So it's either if you install your own equipment, if you're a contractor who installs equipment, you know, it's on you to be able to have that documentation. It doesn't mean you're creating it, but you have to have that documentation upon installation, you know, so that you're not installing it where the SCCR is less than the available fault current. So I don't know if there's any, I want to make sure no questions came in. I usually get questions about the responsibilities associated there.
I don't see anything right now, Christy. It looks like no questions.
Okay, great. Hopefully that just means I explained it well enough the first time. Okay, so that is for the changes made to industrial control panels. It's in Article 409. This is Article 430 of the NEC. There was a change, just a slight change made here for drives. Well, I know a lot of people use drives. So really the most important thing here is this has to do with if you try to mount a drive separately from the fuses or circuit breaker, the protection that you are using for it. So this might be an example, you know, I think of this maybe in like a water wastewater environment, or you think about it in maybe a conveyor where you put the drive physically closer to the motor instead of in the industrial control panel. So if you do something like that, where sometimes you mount that drive separately, it's just really, really important that whatever you are feeding it with, so whatever the overcurrent protection is in front of it, it must have both overload and short circuit protection. So it's got to be like a class J fuse if you're using a fuse, you know, class T fuse, a class fuse. Or it has to be a UL 489 molded case circuit breaker. What it cannot be is a device that's short circuit protection only. So that might be something like a high-speed fuse or a semiconductor fuse, or a motor circuit protector, which is that breaker, looks just like a breaker, but is only short circuit protection. It doesn't have the overload. If you're going to protect your drive with one of those, a short circuit only device, it must be in the same assembly as the drive. If you are feeding a drive outside the enclosure, you must use a overcurrent protected device that has both short circuit and overload protection. If you're using only short circuit protection in the same assembly. So this usually isn't that big of a deal. It's not that hard to just feed it with class J fuses, or, you know, class T fuses. A lot of times that's what's specified in front of the drive anyway. But was an addition made in 2017, so I just want to make sure everyone is aware of it. And the other thing happening with drives, so the listing for drives traditionally has been UL 508C. That is the listing that drives get. It is transitioning to UL 61800-5-1. Why are they changing it to this much longer and harder to remember number? They're doing that because that is the IEC code for drives. So they are harmonizing the UL and the IEC standards for drives. For drives, 25 horsepower and less, you'll probably see no changes whatsoever. Above 25 horsepower, you might start seeing a different overcurrent protective device being specified in front of it. So it's not necessarily that the short circuit current rating is going to go down, or it won't be a high short circuit current rating. It just means that the device that you have to use in front of that drive might be different. So I always highlight this. Just, you know, you might say, I've been using this drive for 10 years. I know that I'm supposed to use, you know, this breaker in front of it, or whatever it might be. Just know that even older drives are transitioning to this new standard. And as a result, that device that's specified in front of it might change. It might not change, but it might change. And so just if you're, you know, you might think I've been using this drive for, you know, 10 years. I know what goes in front of it. Just look up the installation instructions, the updated installation instructions that went into effect this year. So, and just make sure that overcurrent protected device hasn't changed. 25 horsepower and below, most of them did not. Above it, a lot more of them have. So in particular, just again, verify in your installation instructions in your manual that it hasn't changed to a different fuse or something like that in front of the drive. They changed the test for short circuit current rating, became a little bit harder to pass depending on what that device was in the first place. So just letting you know, be aware of that transition and double check that overcurrent protective device. So I don't know if anybody on this call is a manufacturer of HVAC equipment, but it essentially got the same treatment that industrial control panels did, right? It got the same modifications made. The SCCR is supposed to be marked on the nameplate. That's not, particularly new. They did remove some exceptions there. So it used to be that if it was a 60 amp or less piece of equipment, you did not need to have a short circuit current rating, and that exception was removed. So now all HVAC equipment, unless it's cord and plug attachment type, should have a short circuit current rating. And then again, they added that ability to, provide documentation of what that available fault current is. So determine what the available fault current is, document it. Do not install where the SCCR is less than the available fault current. So again, we want to make sure everything is being installed properly. So this is basically the same thing that we had for in Article 409 for industrial control panels. We have in 440 for HVAC equipment.
Hey, Christy, we do have a question.
Yep. Let me see. There we go. I just want to classify if a Class J fuse is used, that is sufficient as opposed to using a short circuit and overload. Yes. So a Class J fuse, any fuse that has a class designation. So if you see the word class in front of it, that means it has both short circuit and overload. So you can just use that. Sometimes you can use in front of a drive. A lot of times drives have overloads built in, and so you can use a fuse that has short circuit protection only. But if you're doing that application where you're feeding it outside, then you need something like a Class J where you have both the short circuit and overload. Great question. That clarified things. And then our last article here in the NEC is going to be industrial machinery. So industrial machinery falls under Article 670, SCCR marked on my nameplate, plainly visible, same thing as with the industrial control panel, field marked with that available fault current. So it's going to be, as opposed to just a documentation of it, it's actually field marked. I believe the reason they field mark industrial machinery is because it moves a little bit more. So if you move the piece of machinery, you're supposed to recalculate that, the available fault current again at that location. And don't install where the SCCR is less than the available short circuit. So again, this is really just writing in an enforcement method for code that's already existed. So, sort of the net effect of a lot of these code changes is really just that SCCR is a lot more visible. It's something that people are caring about more as a result of these changes. Hopefully it's been something you've been paying attention to already. Hopefully it's something that everyone's been paying attention to before, but if not, now it's just sort of being elevated in visibility, something that people are caring about more now that you have to actually know what that available fault current is, that you have to, design the short circuit current rating to. And then the last thing, so they added in 2017, for anyone on here who is, building industrial machinery. If you build industrial machinery with safety interlock circuits, you must have surge protection installed. So if you have a safety interlock circuit, right, that's going to obviously be an electrical safety interlock. Then you must have surge protection. This is the way it was worded in 2017, which is really vague. It doesn't tell you where the surge protection needs to be. Does it have to be only on the safety circuit? Does it have to be on the whole panel? They actually added some clarity in 2020. So it's just in the safety circuit. If you have whole panel surge, that would count, but specifically just the safety circuit has to have the surge protection. So you can use something like that one pole device that you see, that blue. It's type 4 protection, so it's just for that safety circuit. But if you have a safety circuit, you have safety PLC, you have an e-stop, you have a light curtain, something like that, you were supposed to have surge protection on that circuit. Another thing they added in 2020, so a lot of safety circuits are 24 volt DC. And they go through a power supply, and many power supplies have built-in surge protection. And in the 2020 NEC, they said that counts. So if you have a power supply with built-in surge protection, you've already met that. You can check this box of the code as well. So this is sort of a change that I feel like a lot of people just were not made aware of, but there's a relatively simple solution. You can just put this like one pole surge protected device in there, meet the code in a minimal amount of space and cost. I just want to make sure everyone is aware of it. So with that, we're going to go back into, short circuit current rating, why it's important. We did a survey a couple years ago, and 56% of equipment manufacturers said that they designed to the minimum 5 kA rating on their industrial control panels. And that kind of asks the question, how much do we need? How much short circuit current rating is enough? Well, we also took an analysis of a bunch of transformers. So, Cooper Power Systems builds the large substation transformers. And we said, well, what's the common fault current at the secondary of transformers? We took 16 months worth of transformer quotes, came up with a plot of what that fault current output is, and said, what does it look like? And you can see here, you get a lot of that 65 kA, good amount of 35 kA, but it's a pretty, spread out range here. Now what else we did here, right? So obviously most of our equipment does not go directly on the secondary of the transformer, right? There's some impedance between myself and the transformer. Sometimes it's a whole lot. Sometimes it's not. It depends on how far away we are from the transformer, what type of conductor, etc. So we put a dash line in there, and that represents really, that impedance that would normally be between myself and the transformer. So it shifts everything over a little bit to the left. And then we plotted that survey result, that survey data. And you can see, right, 56% were at 10 kA or below. And sometimes 10 kA, 5 kA is all you need, but many, many times you need more than that. You might not need 100,000, but you might need more than 5 or 10 kA. So it's just really important that we know what that value is, know what that available fault current is when we're there, so we can design the SCCR to that point. We really, really don't want to be in that place where the short circuit current rating is less than the available fault current. That's where we get, fire, projectile, shock hazards, and we really, really want to avoid that. People are at risk, the equipment's at risk. Definitely a danger there. So with that, I'm going to go into UL, right? So the UL listings that govern short circuit current rating for industrial control panels. That's UL 508A. I mean, I don't know how many are officially UL 508A panel shops, but even if you are not a UL 508A panel shops, the only accepted method to determine short circuit current rating is the UL 508A as supplement SB method. So even if you're not designing a UL 508A, if you're not putting that sticker on it, to determine the short circuit current rating, you still must use UL 508A supplement SB to determine that value. For drives and power conversion equipment, we talked about this. It was UL 508C is transitioning to UL 61800-5-1 to harmonize with IEC. Just again, be cognizant of what upstream overcurrent protected device you are using for that. I believe a lot of Rockwell drives already use a class fuse in front of there. They use a lot of the class J, the DFJs, some class Ts. So those are probably not going to change. But again, just double check all of those for about the next year, and make sure that device specified in front of it hasn't changed. And then control components are often listed to UL 508. So not UL 508A. UL 508A is the assembly. A is for assembly, right? So that's for the entire industrial control panel. UL 508 is for a lot of the components that go inside the panel. That is also transitioning to UL 60 947-1, another harder to remember number, but we're harmonizing with the IEC here. There are no major changes happening here. So, the testing requirements and things didn't change. It's really just the number that's going to change there. So just in case you see that number pop up, know that that's what it means. If you see that UL 60 947-1, that used to be UL 508. And then one other sort of major change made in UL 508A, an updating to nameplate marking. I swear a very large percentage of questions I get is about nameplates, but they actually changed the location of the nameplate info with short circuit current rating. So the first change they made, there were a couple iterations of this, but the first change they made is they said that the entire nameplate had to be visible without opening the door or cover. They got a lot of pushback from that. Nameplates can be really large. There might not be enough space. Sometimes you put your manufacturer name on that, and maybe you sell to a competitor in a different division and they don't want your manufacturer name on there displayed on the outside. So they actually clarified it so that there's 3 pieces of information, which would normally go on the nameplate, that have to be visible without opening the door or cover. And those 3 pieces of information are the full load amps, the voltage rating, and the short circuit current rating. So all of the rest of the information that would normally go on a nameplate could still go sort of on the inside of the door type thing. But those 3 pieces of information should be visible without opening the door or cover. They also added the environmental type enclosure in there. So it was more of, I think it was listed somewhere, but it wasn't listed somewhere else, and they just, it clarified basically that the environmental type enclosure had to be on there. So here's sort of the breakdown of everything that should be on your nameplate according to the NEC. So NEC 409 requires what's listed there, and UL 508A nameplate is on the right. These are pretty much the same. The biggest difference is going to be that UL 508A adds the largest motor FLA. So you need the total FLA, but you also have to have the largest motor FLA is added. UL 508A, it's the maximum voltage as opposed to the supply voltage too, which those may or may not be the same thing. That's kind of one of the other changes. But this is what's there, and what you can see in bold on the right, that's what should be visible without opening a door cover. A lot of people, it's a whole lot easier just to make one nameplate, stick that whole thing on the outside, but if that doesn't apply to you, you at least need voltage, FLA, and SCCR on the outside. Everything else can still be on the inside.
Hey, Christy, looks like we have another question in the chat.
Okay, let's see here. To determine the SCCR of a control panel, do we consider the ratings of all devices, active and passive, or just certain devices? Yes, we consider the ratings of every device in the power circuit. So we're going to go really, really in depth into all of the weeds on that next week. So when we're determining the SCCR of yes. So everything that is in the power circuit, so we can ignore the control circuit. But again, we'll go really, really in depth into that next week. And for the end, is this presentation available? Yes, I will. I should have mentioned that in the beginning. I'm going to send a copy of this presentation to Nicole, along with a couple links. I have some links that detail those changes to the NEC that were made as well. And she'll send that out to everybody who attended. So both great questions. So this is, just about wrapping it up here, this is a case study. This is really what we all want to avoid. This is the situation we do not want to be in. So this was a manufacturer of you know, the refrigerators and the freezers that are in the section of the grocery store, right? The best section because it has the ice cream. So they manufacture that equipment. The equipment specification did not list as short circuit current rating requirement. That is extremely common, right? That's just not on the radar of a lot of people whenever they are writing that specification. So no SCCR requirement. The OEM's standard equipment was rated 5 kA, so that's what they quoted, that's what they built, that's what they, you know, delivered. The actual fault current calculated was 35 kA, right? So they actually once it was installed and they figured out the actual fault current was 35 kA. Well, an inspector failed that. In this case, you know, new grocery store coming in, there's actually an electrical inspector involved. He sees that, he fails it, he red tags it. You can't open the store until you fix this piece of equipment. Now, and of course, fixing this piece of equipment in the field is really, really difficult, right? If you're going to try to raise the SCCR, you might have to change out a lot of components. These components may no longer fit in the same box that they fit in before, so you have to get a whole new box. Very time consuming, very expensive. Sometimes you can install an isolation transformer in front of your equipment. So an isolation transformer can lower that fault current. You of course have to make sure that it lowers the fault current enough, right? 35 down to less than 5 kA is a pretty big reduction. So you're going to have to make sure it reduces the fault current enough. You have to make sure there's a place to put an isolation transformer. And, you know, installing a transformer can add other issues like voltage drop, depending on where you are. And it's really just a whole lot less energy efficient to do something like that. But you're really limited to very, very few options, something along the lines of installing a transformer or changing out components in the field. And a lot of times if you change out components in the field, it depends on how your UL listing works or how much your you know, your inspector or your end user cares about the UL listing. But if you ship out a piece of equipment and it has an SCCR on the nameplate, you are not allowed to change that SCCR nameplate in the field unless you have a specific type of listing associated with you, and most do not have that. So if you are not able to change the SCCR in the field, you could change out components and say, okay, now this has a 35 kA SCCR, but you're not allowed to change that nameplate. So you have to call in like a third party, like a TUV, CSA, UL. You actually have to come in, have them come out, inspect it, verify the SCCR is different, and then they can change it. And that's really expensive, really time consuming. You know, and this is a project where, hey, there was no SCCR requirement. So, you know, you could argue this is in no way the OEM's fault. They did what a lot of us would do in this situation. They just quoted their standard equipment. But if this equipment is the reason, you know, that store's not opening, have the delayed opening of the store, larger product costs, right? They're going to get the blame for it, even if it's not their fault, right? They're going to say, oh, you should have known. Why didn't you ask if it was higher? Why didn't you, you know, not that that's fair, but that's a lot of times what happens in the real world. So we just want to make sure really that we avoid this situation altogether. That's the goal, right? We want to ask for that available fault current up front and design the equipment to that, because fixing this in the field is really, really difficult. You know, and you might be able to have lawyers point at each other to see who's going to pay for it, and it's going to be okay, like it'll be fine, you'll be covered. But it's still a matter of your reputation, you know, on the line here as being a smooth installation, whether it's fair or not. So again, this is the reason we want to make sure we have adequate short circuit current rating up front, because fixing it in the field is a nightmare. There are very, very few good options for fixing it in the field. So we always want to make sure we have that adequate short circuit current rating up front. So with that, right, so the sort of wrapping up, I told you today was the shortest presentation. So in the design and proposal phase, right, ask the customer for the short circuit current requirements. You might also want to determine a standard short circuit current level, right, 80-20 rule. Whatever your standard short circuit current rating level that will cover 80% of all of your applications, right, and And depending on the type of equipment you build and the type of systems they go into, that might be 10 kA, that might be 65 kA, right? It's really going to depend. It's really, really application specific. But determine the standard SCCR. So, even if you don't have a requirement, you could probably make an estimated guess. Hey, most of the time people need 22 kA. Let's make it 22 kA. We know it'll be okay that way. And you can get some economies of scale going on when you do something like that too, where you have sort of a standard level. And of course, review and analysis. We want to use high fault SCCR components and current limiting over current protective devices to get that higher SCCR. We'll talk a whole lot more about that next week when we actually go through UL 508A and determine that short circuit current. That's the longest one of these. That one's about an hour and a half just to go through UL 508A, but we go really, really in depth there. So that is what is up next. Again, we'll send out a copy of this presentation to you, so you have a copy of this, and I really, really hope you join us next week, where we go through UL 508A supplement SB, and we calculate the short circuit current rating of an industrial control panel.